We make covariance between groups X and Y easier for us to interpret by dividing the covariance by the respective standard deviations of these two different data series. And that's all well and good, but it really leaves a question completely unanswered. How is it that covariance could take on any value whatsoever, negative infinity all the way up to infinity, and yet correlation coefficient is bounded between -1 and +1 inclusive? Let's jump into some data and we'll take a look, get the answers together. Lines on Clay users, please come in and experiment, play around with some of these values, in particular this value here, and this value down here, to get a sense for how correlation works a little better. You can just make a copy of the file that we've linked to you in the course. So what I've done here is I've come up with 20 different observations, and this is all just made up data. So I've got observations from group X. And the first case that we see, we have a perfect mimicking, right, in group Y. So when X was 2.5, Y was 2.5. When X was 3.1, Y was 3.1. Effectively, this is asking, well, how does X covary against X? How does X covary against itself? And what we find is that the correlation is 1. It's absolute perfect correlation because correlation is a measure of linear association between two variables. Well, if my variables are completely in lockstep with one another, well, then of course they're going to have a perfect linear association, one with the other. Okay, great. And here's something that's pretty interesting. What if we change the slope? And what if we change the intercept? Well, let's just handle the intercept first. Let's all of a sudden make 30 the value of the intercept. Well, the line went up. It's a little different than it was before. It no longer goes through the origin. But yeah, still there's a perfect linear relationship. It's a positive relationship. Correlation is 1. What if I make the slope, say 5? Once again, that changed the axes, the y-axis, but I still have a perfect linear association between these two variables. The only thing that's kind of different is what if I put in a negative slope? First of all, we'll see that correlation doesn't change based on the intercept. Let's put in like -20. I put in -20 and I still have a positive linear relationship between X and Y. Well, what happens if I put in any negative slope? I'm going to put in -2. Well, now all of a sudden the correlation goes to -1, a perfect negative linear association. And notice this, other than the negative sign, the correlation is completely unimpacted by the slope. So if I put in -5, well, the correlation is still -1. If I put in -0.25, well, the correlation is still -1. There's a negative linear relationship, but it's a perfect linear relationship. Now, I'm going to go back and I'm going to make the slope 1 and I'm going to make the intercept 0. But now I'm going to create this new data series and it's going to have a wiggle factor. I've essentially added some uniform random number between 0 and 1 times whatever I put in for the wiggle factor. And there's going to be this new data series over here in green. And let's just see what happens. Right now, with no wiggle factor, they're once again perfectly the same. They line up. But if I put in a wiggle factor of, say, 0.5, well, now all of a sudden, a random number somewhere between 0 and 0.5 is being subtracted from, I could have just as easily added it too, but it's being subtracted from my observation Y. And now all of a sudden, it doesn't line up quite as well as it used to, does it? We have a trend line going through here that I've added, and then this R squared, which is really reporting the explanatory value of X and Y. How well does variation in X explain variation in Y? That's news for another day, but it's R squared is the correlation coefficient squared. Well, what happens if I up the wiggle factor? Let's take the wiggle factor up to 2. Well, now there's a little less good of a linear connection. And you see that R squared went to 0.888. The correlation here went down to 0.94. What if I make the wiggle factor 2 but 5? Well, the correlation is falling, right? It's now 0.549, and these dots are all over the place. If I take that wiggle factor higher and higher, well, this line that is supposed to best represent the data becomes less and less good of an explanation, less and less good of a fit for the linear connection between these data. Clearly, when X is going up, it still seems like Y tends to go up, but it's just nowhere near as good of a relationship. So put in a very unscientific way, the closer the wiggle factor is to 0, the more linear these are going to be, and the farther the wiggle factor is from 0, that just these random little side explanations for what's going on with Y, the less good or the less high the correlation is going to be. However, you're never going to correlate better than if you were just to take a perfect no wiggle factor at all and say, how does a variable covary against itself? And when we do that, the correlation is 1. So you're never going to do better than 1. And similarly, if we take the slope and we make it negative, or you're never going to correlate negatively more than -1. And so that's a basic explanation for why, even though covariance can take on any value whatsoever, -infinity to infinity, the correlation coefficient can only take on values between -1 and 1.